Hi guys, this is Mrs. Mendy, and today we're going to talk more about mixtures and some other things that come up in talking about mixtures. Like solutions, separating out mixtures, and then also moles and molarity. And we'll find out more about what that is when we talk about it. Okay, remember that a mixture is two or more substances mixed together, but not chemically bonded. So here are some examples of mixtures. There are a zillion more, okay? And they can be very different, like how well they are mixed, how small the pieces um, are very different, okay? So like this tea, you can't see these particles of tea that are in the solution. Even under a microscope, you wouldn't be able to see those. As opposed to like this pasta salad. It's a mixture, but you can totally easily see the different components. A homogeneous mixture is a mixture that is very finely mixed, even under a microscope. And what we mean by homogeneous kind of depends on the scale that we're talking about. So these are things that look the same um, to your eye, and that's really like the level at which I'm going to ask you to know this. A heterogeneous mixture, so hetero, look at that hetero versus homo meaning same, hetero meaning different. So heterogeneous mixture is a mixture with variable composition. So if you take a sample at a certain spot, you're liable to get different bits. Okay, that's how you know it's a heterogeneous mixture, is because a little a little sample of it will give you different bits. Like if you took a handful of this, if you took a little spoonful of this or whatever, it's going to be different at different places. That's not going to be true for things like the tea and the milk. It's going to be pretty much the same. Okay, so looking at this on the molecular level, and these little circles pretend that they are molecules. A homogeneous mixture, it's going to be pretty even. So if you take a sample of this, it's likely to be pretty much the same, depending on how fine the scale you're looking at. Uh, and a heterogeneous mixture, it's more clumpy. You think of it that way. Separating mixture. So this is a thing that you will have to know. And what you need to know about this is that you separate mixtures by using differences in their properties. So if there's something different about them, you can use that to separate them. And this is kind of a theme in science. Like if there's some difference between any two groups, then there's something that you can use to distinguish between them. Okay, so thinking about this, how would you separate gravel and sand? Well, let's think through. Okay, so a difference in their properties between gravel and sand is the size of the pieces. The sand is much smaller than the big gravel. So you can separate by size. So how would you do that? You can use a colander or some other kind of filter that catches the bigger pieces but lets the smaller pieces go through. How would you separate salt and water? So if they're dissolved together, the salt is dissolved in the water, how would you separate that? Well, think about some of the differences between salt and water. So one difference is their boiling point. So you probably don't even think about salt as having a boiling point because you don't even usually see melted salt, much less boiling salt. But that's only because its boiling point is so high, it's not normal for us to see it. So, but we can separate these out. So you can separate it with heat or evaporation because you can boil off the water. So you can boil away the water. The salt will not boil, it will not evaporate. And so you can separate them that way. So the water can get converted into water vapor. You can catch it, condense it, whatever you want to do. Or if you just want the salt, you let it boil away or let it evaporate. How could you separate salt and sand? So thinking about some of the properties of salt and sand, it's like, well, okay, here's the difference. how they dissolve in water, or do they dissolve in water? Because salt does dissolve in water, sand does not. So we could use that to separate them. So you separate it with water, mix them with water, the salt will dissolve, and you pour off the salty water. So you can just keep doing that because the sand will just not dissolve. You can get it away that way. How can you separate sand and iron filings? So the difference in the properties between regular sand, which is made of uh, silicon dioxide, which is basically glass, and iron filings is their reaction to a magnetic field because iron is attracted to magnets. Whoops. Oh, and I didn't say. Okay, you can separate them with a magnet. I forgot to make that part of the slide. Oh, there we go. Use a magnet to lift the iron filings away from the sand. I just had an extra slide in there. Okay, solutions. Now, solutions, I don't mean solutions like how you solve a problem, not that kind of solution. I mean a very special kind of mixture. Okay, so this is what I mean. A solution is a mixture of two or more substances evenly mixed into their smallest particles. Okay, so the smallest little pieces that they can be, that's a solution. Okay, so it's broken into the individual molecules or atoms, depends what they are. But I mean, not where you have to break apart molecules, but where you're breaking apart associations between molecules. So, say this is a sugar crystal, okay, and these are individual sugar molecules here, showed simplified. So, this chunk here is more than one molecule of sugar. So it's not dissolved into individual molecules. So right here where the sugar chunk is, it's not a solution, even though it's a teeny, teeny, weeny chunk only made of, maybe 2 dozen molecules, still not a solution. So if over here where the sugar is completely dissolved in the water, that's a sugar solution. Okay, so when everything in the mixture is broken down into its smallest components that it can be and still be it. Like you can break down sugar molecules more, but then they're not sugar anymore. They're carbon and oxygen and hydrogen, but then they're not sugar anymore. Okay, okay. Solutions are transparent, not cloudy, because the particles are so small, they don't block the light. So, like this is a solution. This is not a solution. You can't see through it because the particles are big, relatively big. They're actually, they're quite small on a human scale, but they're big enough to block the light as it goes through. Now, transparent does not mean water colorless, okay? You can be transparent and have a color like Kool-Aid. Kool-Aid is a solution, okay, if it's clear. Solutions are also one color, not a gradation. So you see how this is like grading from light blue to darker blue? That is not a solution because in a solution, the particles are evenly dispersed, so it's mixed up. So if you mix this up, you might get a solution. Okay, but right now this looks like they just put the stuff in the bottom of this liquid and it hasn't completely dissolved yet or it just hasn't mixed evenly. So you could mix it. So it's not a solution until you mix it and it's all nice and clear and even. Okay, in a solution there are two parts. The solvent, or solvent is how you would say it. I'm saying the vent part harder so that you can hear the difference. That's the liquid that the stuff is dissolved in. And the solute is the thing that is dissolved, the stuff, the other thing. There's usually more solvent than solute. Okay. Again, this is not a solution yet because look, it's not evenly colored. But if you swish this around, this looks like it would dissolve. Okay, we measure solution concentration using molarity. Now that's a new term. Make sure you write this down. Okay, molarity is moles of solute. Remember, that's the thing that you dissolve, divided by liters of the finished solution. Of the finished solution. Okay. Now you may be saying like moles. What is this? What is this? What does this mean? And I would say Hold that thought for a second. For now, just think of it as how much of the stuff, and we'll say more about this in a second, but this is kind of a bigger topic. Okay. And for liters of solution, notice that this is not liters of solvent. It's not that. It's liters of completed solution, like after you've dissolved all the stuff in it. Okay. Which is kind of weird. And this is just because of how it's easy to make solutions and have them be precise. Okay. So if you're making like sugar water, this doesn't say add so many moles of sugar and so many cups of water. That's not what that is. It's saying like you put enough this much sugar in enough water to make say 2 liters or whatever. So the completed solution, that's what this is measuring. Okay, the unit for molarity can appear 2 ways. Okay, sometimes you will see it moles per liter. That's true, but more often you will see it as just capital M and that you say it like as molar. So, for example, a 12 molar aqueous solution, and aqueous means that water is the solute. Um, oh my gosh, the solvent. Oh, geez Louise. It's solvent, not solute. Because solute is the NaCl. Anyway, a 12, because I'm talking about molar, so ignore this part. A 12 molar aqueous solution of NaCl has 12 moles of NaCl per liter of finished solution. How do you make a molar solution? Okay, so you'd put the right number of moles of the solute in a volumetric flask like this. So volumetric flasks have this little skinny line at one point, and then you dissolve a little in the solvent, in a little of the solvent. So like if you're putting water, so you put your stuff in the bottom, you put some solvent in it, swoosh it around until it's all dissolved, and then you put in solvent, like more water, into exactly up to the line. Okay, and then you mix it around a little some more to even it out, and you're ready to go. So that's why it's easier to know like the finished solution, because it's easier to do that way. Otherwise, you'd have a different amount of solution each time, and it wouldn't really be per liter of the solution. It just makes the math easier. That's why we do it this way. Okay, so now let's go back to what moles are that we talked about in molarity, and I just said this means sort of amount. But let's talk a minute about moles. Now, I don't mean these kinds of no moles. So not mole sauce you can get in a Mexican restaurant, or if you're lucky, your mom makes this. Um, Not mole, the tiny animal that makes burrows and eats worms. It's a different thing, completely different. Unfortunately, the same word. Okay, so let me start from this. We know how much an atom weighs from the periodic table. We haven't talked really about the periodic table, but you've seen them. And so one of these numbers on the periodic table is how much the atom weighs in atomic mass units, which is about the mass of one hydrogen atom. Hydrogen's the smallest. So it's like, how many of the smallest atom does this weigh? Pretty much is what that means. Okay, but instead of dealing with atomic mass units, because how do we know how much a hydrogen weighs? Let's convert it to grams. That way we can use a balance to measure how many atoms of something we have. Okay, but the mass of one atom or molecule or one, particle is so teeny weeny tiny 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 that it's really hard to measure it in real life. Okay, so for example, one carbon atom is about 12 AMUs, atomic mass units. So it weighs about as much as 12 hydrogens. But in terms of grams, that is 1.9926 times 10 to the negative 23 grams. So tiny. We can't measure that. We can't measure that. It's so small. So the solution is let's measure a bunch of atoms at once so that they're heavy enough to measure on a human scale, with regular equipment. Okay? So measure this big pile, not just one. And we'll just say, "Oh yeah, that we can do." That's what you do when you measure any, tiny thing. Like when you buy grapes at the grocery store, you don't weigh one grape. You put all of the grapes together and you weigh them like that. That's how they know how much you have. Okay, so the name of the giant number of atoms we measure is called a mole. Okay, so it's just a number that we pile up so that it's big enough for us to deal with. Okay, so a mole is just a number of something, like a dozen. That's another word for a certain number. So a dozen is 12 of anything. So a dozen donuts is 12 donuts. A dozen eggs is 12 eggs. A dozen roses is 12 roses. So it's 12 of anything. A mole is 6.022 times 10 to the 23rd of anything. We talk about it in terms of atoms or molecules, like a mole of whatever this is of hydrogen, a mole of oxygen, a mole of glucose, anything will mean 6.022 times 10 to the 23rd atoms or molecules of that thing. So that number, 6.022 times 10 to the 23rd, is called Avogadro's number. After me, says this guy, Amedeo Avogadro, Italian chemist. I didn't discover it, but I'm just that cool. So they named it after him. Handsome fellow that he is. A mole is a big number, really big. 20 times 10 to the 23rd, that's a big number. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you got a mole of pennies on the day you were born and spent $1 million a second, 24 hours a day, until you died at age 100, you'd still have over 99.99% of your money in the bank. That's how much. A bowl of pennies just. That's how much money that would be. Okay. So just thinking about, let's jump back to molarity. And just because this is a thing that I'll expect you to be able to calculate, but it's only algebra. But let's do it anyway, just to make you relax. So if you mix 46.7 moles of sucrose to make 2.5 liters of aqueous, water-based solution, what's the molarity of the solution? Okay? Well, first thing you do, anytime you use anything with an equation, is you write the equation down first. Every time. Every time. Every time. Okay? You guys, I'm not kidding you. Do it every time, and then you will not make a mistake. If you don't do it every time, guaranteed the time will come when you will make a mistake, and it'll probably be when you're in a hurry, like on a test or something. So write it always. Okay, so molarity equals moles of solute divided by liters of solution. So the moles of solute, that's the stuff that you're dissolving, and the liters of solution you have left. Okay? So from here, you just plug in from the question. So 4.67 moles of sucrose divided by 2.5 liters of solution, and then it's just easy. Okay, so you just plug this into the calculator, you get 18.68 moles per liter, or you would say, since it says what's the molarity, you'd put 18.68 capital M. If you put lowercase m, that's going to be something different. That'll be meters, and it'll be wrong. Okay, capital M. Okay, that's it for today, and I will see you next time.